Here's something the maintenance industry doesn't talk about enough. The tools are working, the dashboards are live, the predictions are coming in, and yet, on sites around the world, the same failures keep happening. The same reactive cycles keep repeating. The same gap between what teams know and what actually gets done keeps showing up. So the question worth asking is, why? Why, with new and existing technology, is the problem still there? To answer that, it helps to think about how value actually moves through a maintenance system. In some cases, it starts with data. The data has context around it. Context becomes insight. Insight can drive a decision. That decision can become a work change. The work change can be executed. And if everything works the way it should, feedback from that execution loops back and makes the next decision smarter. That's the chain. And value only appears at the end of it. Here's the problem. Most tools today are genuinely good at the beginning of that chain. They collect data well. They detect patterns. They surface anomalies, sometimes early. Technologies from companies like C3 AI, Siemens, GE Vernova, and Palantir are real examples, and the technology works, but too often, it stops at insight. It hands the engineer a prediction and considers the job done. But a prediction by itself doesn't reduce downtime, not even close. There's a useful way to think about this. Separate what a tool controls from what it doesn't. Controlled value is the outcome a tool can directly influence. A troubleshooting assistant that helps a technician find the right diagnosis in 2 minutes instead of 20 has created controlled value. The tool owns that. Dependent value is the bigger outcome that might improve if everything else in the system aligns and the insight is acted on. Lower downtime, higher availability, and reduced maintenance cost. Those outcomes are real, but they depend on spare availability, access, production windows, workforce capability, execution quality, and a dozen other things the tool may not control. This distinction matters because, without it, tools end up promising outcomes they can't deliver. When the numbers don't move the way the pitch deck suggested, trust breaks down and adoption stalls. The better question to ask about any tool is simple. What part of the chain does this actually control? So where does the chain break? It tends to break in the same places across almost every site. Take FMEA as an example. Most teams have one, and tools can genuinely help by drafting failure modes, connecting work history to known risks, and flagging where the strategy no longer reflects reality. That's useful, but an FMEA that never makes it into the CMMS, never updates a PM task, and never changes an inspection routine is still just a document sitting in a folder. The value was always downstream of the analysis, not in the analysis itself. Data quality is another example. It's not that industrial sites lack data. It's that the data sometimes isn't usable. Asset names don't match across systems. Failure codes are incomplete. Technician notes are written in a hurry. Context is missing. Cleaning and structuring that data can be one of the most practical and measurable things a tool can do because the value chain is short. Better data can sometimes lead directly to better decisions, especially in inventory management and spare forecasting. Then, there is reactive maintenance. Predictive tools are built to reduce it. They can, but only if the prediction becomes a decision and the decision becomes a work order that gets executed. A forecast that nobody acts on is just earlier visibility. It doesn't change the outcome, and prioritization is another example. In theory, it is driven by criticality models and risk frameworks. In practice, it is often driven by whoever makes the most convincing case in the review meeting. Static frameworks don't move with real-time risk. And even when a tool gets the prioritization right, the work still has to be approved, scheduled, resourced, and done. The tool controls the ranking. It doesn't control what happens next. The pattern is the same everywhere. The insight exists. The action doesn't follow. The answer isn't one giant system that closes every loop at once. That's too complex, too slow, and it touches too many teams and approvals to build trust quickly. The answer is smaller. It's about closing specific gaps where the distance between insight and action is short enough to bridge. Think of these as micro loops. In master data management, messy material records get cleaned and deduplicated. That surfaces consolidation opportunities. That avoids an unnecessary purchase. Short chain, clear owner, immediate measurable outcome. Value unlocked. In diagnostic support, a technician gets a fault symptom matched to relevant procedures and prior work history. The diagnostic path gets faster and more informed. The tool controls that. The outcome is real. Mean time to diagnosis is reduced. In PM optimization, a failure mode connects to RCM logic and produces a draft strategy change that is ready for an engineer to review. Not automatic, review ready. The engineer still decides, but the distance between analysis and action just got a lot shorter. Value flows downstream. In data cleansing, a technician's note gets structured into a proper failure code. The failure history gets richer. The next analysis gets more reliable. One small loop, real value downstream. Work order patterns flag a recurring failure before the next breakdown forces the conversation. A strategy review gets triggered. The team gets ahead of it instead of reacting to it. None of these close the entire maintenance system, but each one moves someone closer to a real action in a place where the value is clear enough to measure. There's one more thing worth saying clearly. None of this works if engineers don't trust it. And engineers don't trust outputs that arrive without explanation. They need to see the reasoning. Here's the asset. Here's the failure mode it relates to. Here's the evidence behind the priority. And here's the assumption being made. With that, they can inspect it, challenge it, and make a proper decision. That's what decision support means. Not a black box that tells people what to do, but a tool that makes the decision faster, better evidenced, and easier to defend. The best implementations keep the engineer as the final authority. The tool handles the data, pattern detection, and option generation. The engineer makes the call. That's the relationship that builds trust over time. And trust is what drives adoption. Adoption is what actually moves the numbers. So here's the test worth applying to every tool in the maintenance stack. After using this, is the engineer closer to taking a useful action? If the answer is no, the tool is generating more information, not more value. If the answer is yes, the follow-up questions matter too. What action is now easier? Who owns it? What system does it need to enter? What evidence supports it? And what approval is required? Broad claims like improves reliability are hard to measure and even harder to attribute. Narrower claims are more honest and more provable. Reduce the time to turn a reliability analysis into an implementable strategy change. Reduce duplicate materials, cut diagnostic search time, and improve the quality of failure history. If there's one takeaway, it's this. AI in maintenance is no longer theoretical. It is already practical, and it scales fastest when engineers share a common language and track value consistently. That's exactly what we're building with NextGen Maint, a place where reliability engineers can explore practical AI applications in maintenance and see what is already working in the field. Join us at NextGen Maint as we keep exploring real-world AI use cases and the technologies shaping modern reliability.